What's up, peers, and welcome to Join the Wasabikas, a Bitcoin privacy podcast. My name is Max Hillebrand, and today I sit down with Lloyd Fournier, who is a researcher in the Bitcoin cryptography space, and he has made some monumental contributions in not just honing down on a articulation and explanation of these advanced cryptographic concepts, but actually done a fair share of building uh, the actual underlying crypto magic himself as well. Many cool breakthroughs that he has articulated. And here in today's conversation, we dive down into the new cryptography that is going to come to Bitcoin thanks to the Taproot soft fork activation. And this is mainly going to be key aggregation and signature aggregation, which is expressed in MuSig, as well as public key tweaking, which is used in the Tapscript trick to commit to a tree structure of Bitcoin scripts. While then further on, we have adapter signatures, which enable a plethora of things. It's actually a monumental advancement in cryptography as a general to have a provably fair exchange of signatures, making that exchange of signatures atomic. And this, again, is a monumental innovation by Andrew Polstra, again, a Bitcoin researcher, that affects so much more than just the Bitcoin space. This is really cutting edge, novel cryptographic breakthroughs. And of course, this can be used in privacy preserving Bitcoin transactions, namely coin swap transactions. So we dive down that rabbit hole as well. And ultimately then conclude that, well, Lightning Network is a network of coin swaps, and therefore adapter signatures can also be extremely useful to actually improve payment channel construction and the routing through these payment channels in the Lightning Network. Then finally, we speak about discrete log contracts and what that actually means, and how, again, we can use these things with Taproot and Schnorr signatures to, well, do much more efficient gambling, basically, on whatever you want to gamble on. It's a very fascinating technology. Again, we've spoken it here at the Wasabikas podcast a couple times now, but this conversation really is a great overview over the bit more deeper cryptographic architecture of the Bitcoin network. And seriously, it is a marvel to behold. What a beautiful system we have here. So, peers, get ready for this podcast. Hopefully, you're catching it on a Podcasting 2.0 compatible application, not just for this podcast, but for all Bitcoin podcasts. Toss the contributors some sats, value for value. That's always going to be, or that's going to make the future of podcasting stay censorship resistant and a platform for free speech. So I'm very excited now to, without any further ado, give you this full conversation with Lloyd Fournier. So, Lloyd, I'm very excited to talk to you today. How are you, my friend?
Doing very, very well. Thanks, Max. Good to talk to you.
Yeah, so I'm very curious about your early kind of first touch with cryptography and this entire branch of mathematics. Like, what got you into this whole rabbit hole?
Well, what I was doing, I was a trader. So I traded my own money to try and make a living. I was sort of like a disillusioned libertarian, didn't want to participate in society properly. So I was using my money to just try and make more money on financial markets, make a living. It was working out well for a little while. Then I started losing money, but I noticed all these guys were making money on these shit coins. And so I thought, well, why? Of course, I should be able to make money if they're making money. So I went into started trading shit coins, as like many people probably listening to this podcast and in this industry did. And then I got interested in which shitcoin was better than the other ones. So I started doing research, and there was a lot, of course, you come across cryptography and claims about cryptography, and this can work and that can work. And then I started reading papers to see which one was better, and then I got completely sidetracked on the making money thing. Then I got a job in the industry doing as a research engineer at this awesome research lab in Sydney called Coblox. And I learned a lot from the guys there, and we were building atomic swaps. And I was wanted to know more about how everything works. So I started listening to Bitcoin podcasts, and from there I learned more about Bitcoin and the cryptography in Bitcoin, and started applying what I've been teaching myself thus far to the Bitcoin research, and like gradually synthesizing the general Bitcoin narratives and learning more about cryptography. And then I just became fully into doing whatever I could to help Bitcoin flourish with cryptography.
That is fascinating. Because I mean, your proliferation and skill actually in cryptography, like made me think that you have a much like deeper and longer background. But it's awesome that
Yeah,
you
not
actually
not
got
at
into
all.
this.
I did computer science at university, but I can't tell you that I knew much about computer science after that. I knew how to do like a PHP, MySQL application or whatever. I didn't know how to do anything. I didn't know what P and NP was or anything like that. So it took me, it is only recently I started just teaching myself cryptography, like last 3 years, I'd say. And what I can say is, though it's been a short time, I'm much better at this than anything else I've done in my life thus far. It seems to me that I really enjoy this, and by being much better, I mean I just can do it for a long time without getting bored.
Yeah, that's fascinating, right? That when you actually have that motivation, that you don't get bored and you just keep going and going deeper and deeper. So, kind of, what's your meta motivation now that it kind of moved away from gambling on shitcoins?
Yeah, so I was going through a nihilistic kind of. I look back at it and think of it as like a nihilistic phase. And then going even further back, I was like a Ron Paul libertarian in Australia. So, and then, obviously, like he lost the 2012 election in the United States. And I was kind of like, oh, well, there's no way to actually improve the world through politics or anything. So I might as well just try and make money for myself. Then what Bitcoin did and this whole space did, the magic of cryptography did, along with the narratives around Bitcoin. The story that's in Bitcoin is extremely powerful, rooted in history and inspiring. And it sort of like gave me like, okay, maybe the world doesn't have to be bad. It could be improved. It's not the political system that's going to do it, but if we make this currency, this very simple and sort of extremely exciting, but on a technical level, it's kind of as boring as possible. There's 21 million. It's digital gold. It cannot be confiscated, and it cannot be censored. That's a super powerful and simple idea. And if we can just make that work, then life could be a lot better for me. And I've got a kid now and another one on the way. So it could be great for everyone. That's sort of my meta motivation, I think. I'm not sure if I want to be doing this all my life, but I think that working on this is the most valuable thing I can do with my time right now to, make things better.
Oh, fascinating. So, yeah, as you say, you probably won't do it your whole life because, I mean, the big part of being a human is to provide goods and services for money, right? And working on the monetary technology itself is kind of a very niche application that probably or hopefully not everyone in the economy will do because otherwise we don't have any goods and services.
Yeah, that's right. I was very interested in money going into this, like purely, and then I became much more interested in the abstraction of money, right? Regardless, I got a grant from Square Crypto, right? And this was like 9 months ago or so. And at that time, I was completely broke because I'd been just working on the abstraction of money rather than the actual money problem in my life for like more than a year and a half. And so, it would be good at some point to return to concretely creating something, a business or something, with this new system we've built, right? That would be a dream come true. I don't know whether I'm just retire as a farmer and sell my fruit for Bitcoin or my crops of Bitcoin, or I could do something in tech or games or whatever. But it would be nice to use the system that I've been working on and that everyone's put so much effort into. eventually.
Yeah, I think this is like a very profound insight in just the caliber of people working on Bitcoin. Because sure, everyone would like to, provide goods and services and actually earn money, but we all realize that fixing the money itself, the monetary technology, is so incredibly important and will have so many vast-reaching consequences to all those later production stages for consumption goods. That right now, I'm 100% with you. There's nothing more important that I personally could be doing right now other than proliferating the advancement of Bitcoin and privacy technologies. So you're not just thinking about the cryptography and the architecture of these systems, you're actually also writing code. So when did you start actually exploring that area?
Writing code? In general, it was I was at university doing various types of engineering, and became extremely bored with them. And I found that this computer science as an alternative meant that instead of doing assignments or projects where I had to write a lot of stuff, do research reviews and write research papers or write summaries of them, I could just write some like funny Sudoku puzzle or whatever, and then that sounded like a lot better to me. It means so I was not really taking my degree very seriously, and so I thought that would be much less of a waste of my time to do just coding instead of writing as much as possible. And that's what the computer science degree allows you to do. You just pick coding subjects and write the little code problems and submit your solutions, and you get a degree at the end. So that's why I started doing it. It seemed like a more fun way to get a degree, which was something I just had to do for reasons that looking back were probably not good enough. But when you finish high school, you also have no idea what you're doing and why you're doing it. So it seemed like the path of least resistance, and it also gives you a useful skill, right? And I don't really think of myself as a coder, or it's not something I want to do for the rest of my life. I'd be perfectly happy having some young people who are enthusiastic about writing code do it for me if I could, or, if I had enough money and to pay them. But for now, I'm okay at doing it. I'm pretty good, so I might as well use the skill to try and build these ideas I have out. That's sort of where I'm at right now.
Okay, and then when specifically in the Bitcoin space did you go more down the development and contributing actually to those projects?
I got a job at this research lab called Coblox in Sydney, and that's where I started working on engineering stuff around Bitcoin. Okay, so that's for doing atomic swaps with Ethereum and other blockchains. And so this is where I started learning the Rust Bitcoin ecosystem. And then more recently, I've been contributing to the Bitcoin dev kit. But I haven't made that many open source contributions aside from the Bitcoin dev kit. That's probably my main one. I've written quite some code, but mostly experimental code that no one else would really be bothered with. It's like trying out ideas and thinking about things. So that's sort of what I do. Half of the code, at least, is not really intended to be used by anyone. It's more like, does this idea work? I need to make it work in practice. What does this enable? What are the when you actually try to practically implement protocols, you come up with these questions like how many rounds of communication can I actually get this down to, or what keys do I need and when do I need them, and this kind of thing. It's nice to be able to put the idea into code so you can figure out whether it works or not. And you often figure out problems that I didn't catch in the theoretical side of things. So yeah, that's my code is for exploring theoretical ideas, and also, when I can, contributing to the libraries that let me explore the ideas.
Very interesting. So it's more like solving kind of complex theoretical problems and using applied code as kind of mental crutches, right, to figure it out. Interesting.
Yeah, that's exactly it. Maybe some of them will turn into usable products one day, but it's not my main goal.
Why the
I'm very
Rust
happy
programming?
if the idea works, there's someone else to steal the idea and do it themselves.
Why the Rust programming language?
It wasn't. I didn't know about Rust until I needed it for the job. I had no Rust knowledge. That's about 3 years ago. Why Rust? In the end, I fall in love with the language. So the reason it's good is that it's a language that people have thought about very carefully and incrementally, and they're not afraid to introduce features into the language that make the code more efficient. But they're also very careful about what they introduce. And there's also behind it, there's a good deal of understanding of functional programming, like languages like Haskell and type theory in there. And it just takes, instead of it just being obsessed with it, like a language like Haskell and being purist, it like takes the good practical ideas from there and helps you write systems. Design is a systems programming language. So that's what I really like about it.
I hear a lot of good things about Rust, even though I don't have the ability to verify any of it. So let's maybe dive down more of the actual problems that you currently see in the existing Bitcoin kind of cryptography stack. So what are your thoughts on especially ECDSA as we're using it right now?
Well, it's probably a good signature scheme, and that is probably secure because we have recently we had a $1 trillion market cap, and so it means there's maybe not quite $1 trillion worth of Bitcoin there, but like something close to that could be extracted from if you could forge ECDSA signatures, but you can't. So it's at least a secure signature scheme, and we have some theoretical reasons to think it is secure as well, other than just people not being able to break it. The unfortunate thing about it is it was kind of made up in a way that it doesn't reflect some deeper structure, cryptographic structure that comes up in other places. It's just sort of was made up by Tahir El-Gamal as something that kind of just worked, right? It's just like, I put this thing here, multiply by this, invert this thing, multiply by everything, and and you can't forge this thing. Then the other thing, the signature scheme that is much more elegant, although at the time maybe looked also like randomly multiplying things, was the Schnorr signature scheme. It turns out that the El-Gamal signature scheme, which became ECDSA, it ended up being random nonsense. But the Schnorr signature scheme ended up reflecting this more abstract sort of law of the cryptographic universe kind of fundamental protocol. It ended up, Schnorr signature scheme is the simplest instance of a more fundamental kind of protocol called the Sigma protocol. Sigma protocols are used all over the place in cryptography, and Schnorr is just the simplest instance of that, or the non-interactive signature scheme version of the simplest instance of a Sigma protocol. So that's one of the unfortunate things. So ECDSA, we're not linking deeper into other concepts in cryptography. Just this random thing was made up. Schnorr is related to more deeper concepts in cryptography, and then the other thing about that is it's also linear, right? So it's like in this elegant, as simple as possible for a signature scheme to be, using elliptic curve cryptography. And so this linear structure and its simplicity allows you to do more things with it. So that's basically the summary of the comparison.
Fascinating. So can you go a bit more into what this Sigma protocol or concept is about?
Yeah, so Sigma protocols are 3-move protocols. So there's 3 rounds of communication. It starts off with this guy, approver. So it's a zero knowledge proof protocol. Okay, so approver wants to prove something. The common example and the underlying proof that is used, the underlying Sigma protocols for Schnorr signatures is this proof of knowledge of a discrete logarithm, which just is the same thing as saying, I know, proving that you know the secret key to some public key without revealing anything about the secret key. And so it's these 3-move protocols where you first make what we call an announcement. You say, I know this thing, and you give some random bit of data over to the verifier. So the prover sends something random over. The verifier then chooses also randomly some kind of challenge. And we call that the challenge, the thing the verifier sends. So it selects randomly from some set of challenges, a challenge, sends it back to the prover, and then the prover sends back a response to the challenge. Okay, so it's not just challenge, then response, it's announcement, challenge, then response. And so what happens with what the connection is to Schnorr signatures there is that you have this, the verifier is replaced with a hash. So the announcement in this discrete logarithm proof sigma protocol is the what we call the nonce in a signature, in a Schnorr signature. So it's this random secret key you make, you sample it randomly, multiply it by the base point to get the public key associated with it, and you send the public key, this random nonce public key, over as the announcement. And then in the Schnorr signature, you hash that along with a message to get the verifier's challenge. And then you take this, what we usually denote as S, as a response, and you put the announcement, the R value, the random nonce, and the S together, and that is the Schnorr signature. And that's how it relates to this underlying 3-move protocol, with the verifier's challenge that he sends over replaced with the outcome, the output of a hash. So that's the relationship as best I can put it.
That's interesting. But then in the Schnorr signature case, the verifier actually does not talk to the sender of the message.
Yeah, so that's exactly. So it's a different kind of verifier. For a signature scheme, and the underlying sigma protocol verifier is just verifying that somebody knows the discrete logarithm something, right? Whereas in a signature scheme, you're verifying not that they know that someone knows the discrete logarithm. They're just verifying a bit of data is a signature on a message, right? And so those are 2 different verifiers. So the signature verifier just gets a bit of data and verifies. What it does is it takes the R value that's in the signature, hashes it with the message, and sort of plays the role of the verifier, hashes it with the message and the public key and the nonce, and gets the challenge out and sees if the response is correct with respect to the challenge. But the code that verifier runs, the Schnorr verifier runs, is the same as the verifier runs in the final move, in the final execution of the sigma protocol verifier. So stuff that happens up to that point is not the same between them, but the final thing is the same there. So the verifier isn't able to choose the challenge in the signature, right? The hash chooses the challenge, but they do run the same verification with respect to the challenge that the hash chose. Mm-hmm. Does that make sense?
Yes. So the signer of a message actually creates this challenge, the hash, or by hashing the nonce and the message, and then the verifier, in order to verify, must again create that challenge by hashing the message and the nonce.
And the idea is that every single one of these signatures is a separate kind of proof, a non-interactive proof that the person who created this bit of data knew the secret key. And so you can kind of see, if you have a system to prove that you know a secret key, which involves a hash, well, you can just slam a message in there, and then that proves that the guy who has the secret key also says that he signed this message.
Okay, I see. So in that sense, Schnorr signatures are just more elegant than ECDSA, much more pure to the actual concept of what it means to sign a message and verify it.
Right, exactly. They derive from a very universally understood, well-studied zero-knowledge proof. And each signature is just like a little compact, non-interactive zero-knowledge proof over a particular message.
So what are some of the things that are, because of the simplicity of Schnorr signatures, much more easy to implement here than it is in ECDSA?
The one that is most important for Bitcoin is key aggregated multi-signatures. So where we have a multi-signature where all the signers, we together sign under the same public key, right? So we have a protocol, you and I, let's say, we exchange some data with each other and we come up with a joint public key that's a single public key, but it nevertheless requires both of us to contribute our knowledge of our separate secret keys to produce a signature on that public key. So with ECDSA, this is extremely difficult, and only relatively recently have we known how to do it, because people want to do it with Bitcoin. But with Schnorr, we've known how to do it, let's say, mathematically, or and even some protocols to do it for a very long time. Okay, so it's relatively easy to do. Now, to do it in a way that is secure in all settings has only relatively recently been discovered, even with Schnorr. Okay, so doing it securely in all settings has been, ECDSA and Schnorr sort of happened around similar times, but the Schnorr one is much more elegant, and it's called MuSig, and in particular MuSig 2, which is a more recent version, a more recent work, and this allows you to do that. So have all these different people, no matter who they are, and in what setting we are in, and what we can get them to prove about their key. So we can even do it, like the important distinction here, and what we're talking about, like I'm talking about hand wavy about these settings. What we want to be able to do eventually, right, is be able to take all these outputs keys, right? So these Schnorr keys on the Bitcoin blockchain, and let's say I've got 7 addresses and I own money in all of them, right? I want to authorize a spend from all those 7 addresses into, like, let's say I send it to one output with a single signature. Okay. Now, what we need to be able to do is make sure you can do that with the outputs you own, but you cannot, spend someone else's outputs with that single signature. That is tricky, and so you need a way of generating that joint key that creates that single signature securely when you cannot even interact necessarily with the person who created those outputs on the Bitcoin blockchain. Okay. You cannot get them to prove stuff, or you could get them to prove stuff if you're the single owner, but that's too much data on the blockchain and you defeated the purpose, right? So you don't want any proofs. You just want, like, I want to join all these output keys into a single key, create a signature under all of them, and we need to be able to do that securely and make sure you cannot spend anyone's money. That's the long-term goal, and that's not in the recent Taproot Schnorr proposal, but if we can get that, that means that's pretty much the holy grail of this key aggregation, is to be able to do that securely. And we certainly can't do that with ECDSA ever, I would say. So yeah, definitely never on that one. And so that's the thing we can do with Schnorr relatively well now, and we will never be able to do it with ECDSA.
Okay, very interesting. So there seems to be kind of 3 epochs of this. First is the current Bitcoin script, right, where if you want to have a multi-signature, you have to reveal, for example, 3 public keys on the Bitcoin blockchain in the script, and then 2 signatures in the witness of a transaction.
Or use an extremely convoluted 2-party or multi-party ECDSA protocol, which some people are actually doing. Like, this thing actually exists, so people are doing that. But
yeah, and then what MuSig provides, and this is part of the Taproot soft fork, is interactive key aggregation. So that if Alice, Bob, and David have 3 public keys, they can, or one person knowing all these 3 keys, can aggregate them into the single aggregated public key. And we just put that into the address of a Bitcoin output. And now you can only prove a signature to this aggregated public key if you can also sign for all of the 3 private keys, that the individual private keys that actually aggregated to that public key. And only if that actual threshold of 3 out of 3 is met, you can provide a signature. Right, but here you communicate with everyone in 3 or 2 rounds, so it is interactive, right? And then what Lloyd was speaking finally about was the cross-input signature aggregation. So here we have multiple public keys revealed on the Bitcoin time chain in these outputs or addresses, and the signer of a transaction with multiple independent outputs can aggregate these signatures so that there's only one aggregated public key and one aggregated signature for these multiple public keys that are out there. But that is future magic that we'll probably have to talk about in another 5 to 10 years before it's interesting. Probably 20.
Okay, that's very pessimistic. But yeah, there is more work to be done, I think, on the research side there. But yeah, that's the best way of putting it. Yeah.
So then there's one kind of quirk in MuSig that the main paper only works for threshold signatures. For threshold signatures in the sense of m out of m. So it can only be 3 out of 3 or 4 out of 5. So 2 questions here. Is there a limit on how many of these keys can be aggregated into a single public key?
No. If you're doing m out of m, there's no limit. Neither is there a limit for n out of m, but that is another topic, I think. I mean, I haven't studied the n out of m case personally, though I think it seems to be clear how to do it in simple cases, the n out of m. But the m out of m is there's no practical limit other than computational and communication resources.
Yeah, and this is another big win, right? Because in our current approach, where we put each public key onto the Bitcoin blockchain in a script, right? This means that if we are limited by the transaction size and the block size with how many public keys can be put on chain. And I think there is at least a standardness thing in Bitcoin core that you cannot have more than 15 public keys in a multi-signature. And with MuSig, I mean, the sky is the limit. There could be thousands of keys aggregating, and I think the bottleneck is, as you said, right, computation. I don't know, if you have like 1 million public keys aggregated, that will probably take a couple seconds. And then the other thing is probably coordination complexity, right? Being able to send multiple messages among computers that each know these private keys might just take a while and fail often.
Yeah, the script thing is a big important point, because right now there is multisig is obviously a very popular thing to do, and you have companies offering multisig services. But the problem with it is that you get an instant privacy loss just because of the way everyone can tell that you're using a multisig by looking at the chain. And they can therefore know more about that. And there are several companies doing multisig, but you can say, well, he's probably the customer of one of these companies, perhaps, right? You may be rolling it yourself, but I think I'm not sure, but I feel like the majority would be these companies that are helping you do it, right? And so getting rid of this means you cannot get that heuristic anymore, and it makes transactions much smaller. And the sky is really the limit. Just to give you an example, that one thing I'm thinking about is that I'm still haven't given up on this idea of side chains, So one thing I was thinking about is you could have like a side chain, right? Where forgetting about the consensus algorithm of the side chain, but you have let's say many people involved in the side chain, and in order to let's say move funds from the sidechain sort of address, which has all the funds of the sidechain in it. In order to move funds out, you would maybe need a threshold key. And you could even go to very large numbers in a single address, like 10, 20, 30, 40, 50, 100. And you need 90 out of 100 people to say that the funds can move in order for the funds to move. So yeah, that's much, much more powerful than the object multisig.
So do you know what are some of the changes to the actual Bitcoin scripting language that we need to do in order to support these Schnorr signatures?
So the Bitcoin scripting language, as you know it, isn't changing. So you have pay to script hash and pay to witness script hash, and those things are not changing at all. The thing that is changing is you kind of have like a new scripting language that's being introduced that just looks like the old one, with a few opcodes changing around, or new ones. We call it Tapscript. I think it's BIP 342 is the number which it describes it, and so it has what's going on there, and there's just so not much is changing except this object multisig is going away. Even if you want to do multiple signatures, you're getting this. I can't remember the name of the opcode off the top of my head, but it's a push signature onto stack or a check sig on stack thing, where instead of you putting out a list of public keys, you're putting public keys onto the stack and verifying them as you want. So that's the only real change. I think the script is not changing that much. But what it does is like it opens up the door for future changes, new scripting languages or opcodes in a much easier way, because you've got these different ways of extending Taproot. One is the Tapleaf version, so you can create a new Tapleaf version and introduce a completely different script rules in there in a soft fork. So that's probably the biggest impact you'll have on scripting, is now you can introduce new rules and new languages, new ways of doing things without having to introduce a new address format or anything like that. It's just a new Tapleafs.
Then let's kind of build our way towards other cool features of Taproot. And I think one thing that we should highlight is public key tweaking, which is heavily used. So how does that actually work on Schnorr signatures, and is it even possible on ECDSA signatures?
Yes. So so what is happening with Taproot is you're making a commitment. So you're taking your public key and your let's say unmolested public key that you got from your wallet, and you're saying, okay, I'm gonna commit to a script. Well, actually, no, it wouldn't. In the case you commit to a script, it's usually because multiple parties are involved, right? So you're having a multi-signatures or something like that, or some complicated lightning rules or whatever. So you are jointly coming up with a key. So you and your other party, who is part of the lightning channel, whatever you're doing, is coming up with another key, and you're taking that raw key that you've generated together, maybe using MuSig, for example, and you're tweaking that by using a hash to commit to a script, and then taking that hash and adding it back to the public key. And this creates a cryptographic, from that addition, you get back just another public key, okay? So you're going from one public key and a script as input, and you're getting back a new public key. But that public key actually securely commits to both the original public key and this script. And that's what we call this tweaking, right? This adding back this hash of the script back to the public key, or the hash of the Merkle root, technically, of it, which may contain script, back to the public key, and then you've got this tweak. So you've got this public key that's secretly committing to a script that no one else can see. And that's so when you want to spend via the rules in the script, if you want to, because you and your counterparty in the lightning channel or whatever you're doing should both have secret keys, a MuSig secret key, so you can do a 2 of 2 and make a signature without using the rules, whatever. You always have that fallback. And if you're both cooperative, you can always avoid using the script you've committed in the public key. But if you do need to use it, you can just reveal to everyone and say, hey, listen, this public key was actually had a script inside of it. And here's the script, and here's how I'm going to satisfy the rules of the script, the constraints, and now I'm going to spend the coins. That's the really awesome thing that Taproot is introducing.
Yeah, so maybe to summarize, right, we have a tree construction of the Bitcoin script, which is the Taptree, and we get the Merkle root from this, which is just a hash, just a large randomly looking number, right? And then we generate the internal private key and calculate the internal public key from this. right? And again, just a large random looking number. Right?
I think we call that the external one. You already have your internal one.
I think the internal one gets added, like literally 1 + 2 = 3 to the hash of the Merkle root, and that gives you the external
yeah, correct.
key, right?
Yeah.
Or like the tweaked public key, right? And again, tweaking is just 1 + 2 = 3, right? A very, very simple thing. And then if you want to only, like in the cooperative case, spend these coins with only the signature of of this internal public key. So you do not want to reveal a script condition and actually use a script condition like, advanced lightning channel outcomes or stuff like this, or time logs or whatnot, like fallback edge case conditions. If you do not want to use these in the script, you simply produce a signature of that internal private key, and this signature will be valid to the internal public key. And if I understand it correctly, Lloyd, now I just take the hash value of the Merkle root and again add it to the internal signature to get kind of a signature that is valid to the to the tweaked external public key.
Oh, well, that's an interesting idea. I actually hadn't heard that before.
Then it's probably broken. No, I'm curious if that's actually what works.
That would work, I think. You could. You can't just add the signatures like willy-nilly. I mean, you could do it like that, but what you would probably do is what you're really doing. Like, let's take a step back. What we're doing, first of all, let's look at MuSig, right? So you and I both have public keys. We have this sort of key generation protocol, or like it's non-interactive. So we just take up two public keys and we do some hashing and we add them stuff back to each other. So a lot of this stuff is hashing stuff and adding it back to each other. So we take our public keys and we hash them, add back to each other, do the MuSig algorithm, and we get a new joint public key, right? Now what Taproot is like another key generation algorithm on top of that, okay? So when we do MuSig, we're adding our keys together, our tweaked public keys together and getting this joint public key. And then what we're doing with Taproot is we're doing another layer of that. So we're taking a joint public key, we're taking this script, and we're tweaking again our joint public key. And this further tweaks our secret keys as well, right? So the MuSig, we take our raw secret keys, we do MuSig, we tweak them, and to get two secret keys of this, two half keys, let's say, of this joint public key. And then we do Taproot on a Taproot commitment to the script on top of that joint public key, and we further tweak our secret keys. So now for the external key, we both have these half keys, right? So that's the key that goes in the blockchain, and we can do a MuSig signature with these tweaked keys. So we don't really need, we can ignore the fact that it's taprooted completely if we don't want to use the script. Now, if we want to use the script, we go back to our internal key, which we produce from MuSig, and use the signature on that and reveal our internal key. But if we're doing a signature on the public key with the tweaked Taproot public key without revealing any of the script, I think the most straightforward way to go about it is simply to just tweak your own secret key again and produce the signature like that.
Yes. Okay.
Does that make sense?
In the most common cooperative case, right, where everyone agrees, instead of signing with the original private keys and then tweaking the signatures, I wrongly explained it. What actually happens is that you tweak with the hash of the script your private key, and then you have a tweaked private key. Again, 1 + 2 = 3, right? And with this tweaked private key, now you perform the signature algorithm, and that signature will magically be valid for that tweaked public key that is external on the Bitcoin time chain and the Taproot address.
Perfect, exactly like that. Now, I think you just had a new idea that I hadn't thought about, which is to also just do a signature on the tweak and add it back, like to do a kind of multi-signature for it, because it's like this public value that cannot be malicious, right? You could just do a signature, and like Schnorr is linear, as we said, so we could do a kind of Schnorr signature on the tweak, Schnorr signature on the internal key and add them together, and it should be a valid signature for the external one as well. So I think your idea has some good work, but I think the simpler way is to do that. Yeah.
Interesting. Yeah, and that just shows that there can be a lot of flexibility with this crypto magic. But I mean, how it is implemented in the Bitcoin consensus rules, right, is still very strict and specific. For example, this MuSig Taproot path is clearly defined, right? And
yeah, the cool thing, so one of the cool thing I really like about Taproot is that on the security side of things, right, the theoretical security side of things, we actually get this thing on from a securities perspective pretty much for free, which is kind of weird, right? We're saying we have public keys in the Bitcoin blockchain, which are like they're Schnorr public keys, but really they're just points on elliptic curve. It's the same for ECDSA, the same kind of thing. So we have them all up there. And then we're just saying, okay, you can spend it with a Schnorr signature, but you can also spend it with this like weird revealing of this internal key and the hash thing. I mean, that's got to make the funds less secure, right? It's got to make the coins less secure. You would think, right? But what I looked into on this security side of things, it actually doesn't. At least if you're just putting like your funds in your wallet, you can say pretty rigorously, I think, that if you can forge, right? So if you can, like, if I can just take an output on the blockchain and just forge a fake Taproot opening, right? Opening to some script that I contrived, that you can also forge Schnorr signatures. So it's actually the same security assumption. So anyone that can break the Taproot security can also break the Schnorr signature security anyway. So there's no point to worry about it. But that's probably one of the cool things, right? And then, like you said, all this MuSig stuff we're talking about and this Taproot tweaking stuff, all there is in the Bitcoin consensus is a Schnorr verification algorithm.
Mm-hmm.
All this MuSig, threshold, whatever, that's all happening as a protocol between participants. That's not going in the blockchain at all. We just have this dead simple cryptographic Schnorr verifier algorithm, which can verify Schnorr signatures, and we have this Taproot commitment opening verification. And that's it. That's it for the Bitcoin consensus. Yet all the things you can do off-chain now, you can have all these features. We can have adaptor signatures, really simple ones, threshold signatures, multi-signature, key aggregation, and all these hidden script stuff. So that's it's pretty amazing what we've managed to get out with the Taproot idea, and that's a credit to those who came up with them and came up with it and developed it.
Yeah, that really is the beauty, right? It simplifies the verification of a Bitcoin transaction that is being spent tremendously, right? One signature per input, basically. Maybe even one signature for the entire transaction, right? Maybe even one signature for the entire block, right? Depending how crazy we get with cross-input signature aggregation. And that's, I think, that's. But it gives a lot of flexibility to the receivers of Bitcoin, that they can write very complex definitions of who can spend the Bitcoin later, right? So because Taproot is no longer a flat scripting line like the current Bitcoin script, right? The entire spending condition is defined in one single line of code, basically. And you must reveal the entire line, even if you only use a partial spending condition, right? So And Taproot enables to break up the script into multiple smaller pieces, where you can only reveal one out of many, many possible spending conditions. And as long as this one spending condition is valid, the spending transaction is valid. But you do not reveal as a sender which other spending conditions were actually part of that Bitcoin address, which is, again, like the trade-off between verifying, making it as efficient as possible, while still making spending as flexible and as private as possible, is just a very, very, very well-designed system.
I like to think of it, the principle I think it is that Bitcoin should be boring, right? And Taproot, although it sounds exciting, is a way to make the Bitcoin blockchain much more boring. Instead of having these exotic scripts showing up everywhere, you have these really boring outputs that all look the same all the time. No matter what you're doing exotically, with protocols in between the participants, they're doing the work off-chain to make the on-chain stuff boring. And I think Bitcoin is the only cryptocurrency that has this extremely important value, which is the blockchain has to be really boring, has to be kept boring, because it's the money, it's the financial base layer, right? It's the monetary base layer that everything will be built on top of. And so for that, you have to keep it simple and boring and secure. But there are really exciting ways of achieving that, right? And this kind of idea, Taproot, it would only really come up in the Bitcoin research community and effort. Other projects, other shitcoins, right, that you study, that I was looking at and studying, are all trying to do exotic stuff, make their blockchains exotic with all kinds of stuff going on there. This is the exact opposite way. It's trying to be as boring as possible, and you can see there's no coincidence that it's the number one thing on CoinMarketCap. It's because it has the right values and pursues them in the right way. And there's a lot of rigor and time and effort of people spent getting it like that way, from people who really, really care about this stuff. And, it's a funny thing to care about, making something really boring, but that's exactly what the world needs and what people are committed to. So that's just another reason why Bitcoin is the most interesting thing to work on.
Yes, absolutely. It's kind of crazy how nuanced a viewpoint you must have in order not just to understand Taproot, right, but to come up with it in the first place. So yeah, that's a very
totally,
a very interesting kind of prioritization and viewpoint of a mindset. Fascinating to watch what Bitcoin developers come up with. Let's now maybe go into one of the other cool, crazy applications that we can do with that same type of mindset, right? To make verifying as easy as possible, just a signature, right? But doing advanced economical things on top of that. And I think that's specifically like the magic we can do with discrete log contracts. And probably to start out with, it makes sense to first explain what a adaptor signature is.
Okay, yep. Adaptor Signature is this breakthrough idea from Andrew Polstra. I think it was back in 2017, but it's just, it's such an important idea, and it's extremely important for Bitcoin, but it's actually, I think it's generally in the field of cryptography, a breakthrough idea. And so what it is there's a lot of ways of talking about it, and we still haven't figured out the best way, honestly, to talk about it. And neither have I, but the one I like at the moment is a way of locking a signature, or which you can kind of think about as encrypting a signature. So I create a signature and give it to you, but you cannot quite use that signature because it's locked. And there's a condition under which it's locked that you need to satisfy with which to unlock it. And that's really interesting, right? Because that's what we're doing with Script on the blockchain. We're creating conditions that are locking coins, and you need to satisfy these conditions to unlock it. But here, I'm giving you a signature on a transaction, and if you can unlock that signature, you can unlock the coins. You can put that signature on the blockchain. Okay, so that's one part of it. It's like a signature encryption scheme is the way I sometimes go about talking about it, right? Now, the interesting thing, that's interesting in itself. So that's not a small thing either. Being able to do that is not a small thing. It's what I call it, a verifiable encrypted signature scheme. So I can give you a signature. It's an encryption of a signature, but you can verify what is encrypted, which is kind of weird, right? When you get an encryption, how am I meant to know what's encrypted without looking at it? But you can tell that what is encrypted is a valid signature, but you cannot get the signature. That's a really awesome primitive to have. Now, that's pretty awesome, but it's even better than that, because this encryption turns out to be what you can call it one time. You can only use when you decrypt it, right? So you get the unlocking condition of that signature. You unlock that signature. As soon as you broadcast that signature, you reveal the key you used to unlock it to the person who created the signature. Now, normally you might say that that's actually a bug rather than a feature, right? I leaked my key to the other person. But in the context of Bitcoin, that's an amazing feature. Because what it allows us to achieve is this thing that cryptographers have been trying to achieve in weird different ways since they discovered signature schemes, pretty much, which is how do you get a fair exchange of signatures? Let's say I'm delivering you, I don't know, if I'm sending you airline tickets, right? Because you've just made a payment to me. How do as long as I've delivered you the airline tickets and you've got them, I want to get a signature saying, yes, I've taken the airline tickets, right? Same way a delivery man comes to your door and you do a signature, then they give you the parcel. We wanted to be able to do that over the internet. I send you a thing that you wanted to have, and then I get a signature saying that I've done my job properly, right? So maybe your thing is a signature from the airline company saying these are the airline tickets. Now I want a signature. The airline company wants a signature saying you've received this signature. So if you complain to the bank that I never got my tickets, the bank can say, the airline company can say, hey, no, we've got his signature saying he's received them. So this problem, which you call the fair exchange of signatures, it's bugging cryptographers this whole time, right? For decades. They've been coming up with weird schemes to try and fix this. So two people, I send you a message and somehow we both get signatures. I send you a signature. It's better to say it like this. I send you a signature and I get a signature in return saying that you have received the signature. So we both get a signature at the same time. What the fundamental breakthrough with this adaptor signature thing, with this locking of the signature, is that we can actually get that. As long as, in order for the signature to be useful, it is published publicly, so that the creator of the signature can see it on the blockchain. So what happens like this? If I give you one Bitcoin, and this, like, for example, applies to the Lightning Network. I want to give you, well, one Bitcoin is kind of large, so let's say 0.1 Bitcoins on the Lightning Network. I want to only give you the 0.1 Bitcoins. I will give you the 0.1 Bitcoins as long as I get a signature from this other guy giving me 0.1 Bitcoins, right? It's a forwarding payment on the Lightning Network. One of the many applications of the idea. So what with these adapter signatures allow us to do is to get that set up so that I, in the middle, can get at the same time, if I can guarantee, if I get my money taken from me, I will get a signature that allows me to take someone else's money. So now, high resolution on this signature, how does that really work? So, as continuing with Lightning as the example, someone makes, I want to forward the payment. So someone says, please forward this payment, and they give me a locked signature. Okay. Giving me that 0.1 Bitcoin. Now, I can't unlock it right now because I don't have the key. But I know that the next guy in the payment route does have the key. So I forward it to them and I lock a signature to them on the same key. Now, this person does has the key and they unlock it. Now, if they were to go on chain, I would see that on chain and I would be able to extract that key from there that unlocked it and use it to unlock my own payment. So we don't even have to go on chain in this case. You take the funds and you tell me what the key is. I use the key and forward it back to the next guy, and we establish that the funds have been transferred, and there's no case and there's no situation where the one person can steal the money, because of these locked signatures are locked to each other. And if one person takes my money, I instantaneously, upon seeing that signature on the blockchain that they've taken my money, I instantaneously learn the signature, the key to decrypt my own signature, unlock my own signature to get my money. So we've solved this fair exchange of signatures problem with this extremely simple cryptographic primitive called adaptor signatures. There's very little mathematical magic that goes on here. It's like a simple addition, simple modification to the Schnorr sign and verify algorithms to get this functionality. And yeah, we're only now experiencing some of the benefits of this idea, even though it's several years old. We're starting to put things into production with real money on the Bitcoin blockchain, where people are using this for security and to get these the properties that it offers. So it's extremely exciting. That's the long explanation of adaptor signatures.
Yeah, really interesting. So it's somehow like an encrypted signature scheme that allows for atomic exchange of signatures, meaning that either both parties get a valid signature from the other party, or none of them get it. Right? There is no possibility that only one side gets the valid signature from the other, but the other side does not.
Right, and that, strictly speaking, in cryptographic theory, is impossible. Mm-hmm. The thing that makes it possible is that one person does get the signature before the other person, but in order to make use of it, they have to publish it, which will mean the other person will see it. And from that published signature, they will be able to extract something. That's the key thing about it.
So that yeah, even if you have the signature locally on your own computer, right, it doesn't help you anything, because no other full node will verify unless you provide the signature and you put it in a transaction and you put it onto the public blockchain. Right. Only then, if you're in consensus with other full nodes that yes, this coin is spent to your new address, and only then do you actually get the benefit of those Bitcoin. But of course, as soon as you publish this transaction to the blockchain, the person, like the other side of this trade, will see your transactions with your signature, and therefore get the actual data. So that's fascinating. That's kind of like economic game theory or crypto economics. Applied into it's just beautiful. It really is. That's a massive improvement.
Yeah, it's like you said, because this idea wouldn't come from anywhere other than the Bitcoin space, right? Obviously you have very smart people like Andrew Poelstra coming up with this idea, but the idea is so Bitcoiny, right? Because it's about making the blockchain boring again, right? And the important thing, like the thing we haven't touched on, right? This signature that reveals this unlocking key to the other person, right? This signature, this adapter signature that encodes this condition. And when the condition is satisfied, you put the signature on the blockchain. This signature looks like any other signature. Completely normal looking signature. So it's not differentiable. You can't tell like, oh, this is a signature which had a condition in it. What was the condition that was satisfied to get this signature on the blockchain? No, it doesn't. To everyone else, it looks the same. It's only to the signer, like that person that helped create it, that person that created the adapter signature, they can tell the difference. They know what the history of that signature was, and that guy had to have taken this adapter signature that I gave him, this encrypted or locked signature that I gave him, and to create that signature, that's the only way he created that signature, is by unlocking it. That only the person who gave him the locked signature can tell that. And that's like a super important point, right? Because in the end of the day, all you have on the blockchain is just normal signatures again. And yet you had this protocol to create conditions on that signature existing. But once it exists, all the history of what went in to create that signature is gone. It's in the memory hole. And no one can even prove that what went into that signature originally, right? No one can say, oh, no, that was really a signature that had this lock on it and did these things, and to unlock it, it just looks like a normal signature.
Yes, and I think it was easier to get to the concept or to find this conclusion just by looking at existing Bitcoin technology, because the same concept we already made possible with hashed time-locked contracts, right? Where you commit to a secret by hashing to it and putting that hash on the public blockchain and making that spending condition that you can only spend the coin if you publicly reveal that actual secret. Right? And once we have that setup phase of committing to the secret in a spending condition, other parties can rely on that and do that same crypto economical trade. Right? And now the innovation by Andrew Poelstra is to replace signatures with hashes. And it's
hashes with signatures.
right? Yes, hashes with signatures. Yes. Now, is this possible with ECDSA already now?
Yes, it is possible. It is rather awkward, and I helped develop the idea. The idea came from Pedro Moreno-Sanchez originally. He and Ankiet Kate, his co-author, posted something to the Lightning mailing list, like showing that, like, with some great effort that is involved in two-party ECDSA, you can actually do this as well. Then I said, well, actually, let's just get rid of the two-party ECDSA and we can just do that without it, and do the ECDSA adapter signature component of this idea. And that idea has caught on, funnily enough. And we actually have ECDSA adapter signatures. We have it in this library called SecB256K1 ZKP, which is like an extended version maintained by Jonas Nick and other people on work on the Elements project at Blockstream. And so we actually have the code to do this live now and is being used. And so there are some rather big downsides to this thing, but for the case of DLCs, it's perfectly fine to do this until we have Schnorr.
Okay, that's great to know, right? We can already now benefit from this. But again, switching to Schnorr and Taproot will make everything a lot easier. So that's great.
Yeah. So the thing you have to stress is that this two-party ECDSA thing is really difficult, and so we're still using object multisig with these adaptor signatures, whereas as originally envisioned, they would be single aggregated keys and adapter signatures on the aggregated keys. And so one thing we should mention about the history of adapter signatures is they were created for Mimblewimble. So what Andrew Polster had in mind was Mimblewimble, right? So this is this other blockchain architecture that is rather quirky and interesting, but it cannot have any scripting language just because of the way it works. And so he wanted a way of creating conditions on transactions that didn't involve any script, right? And so this is where the idea comes from. And certainly this Schnorr, that makes sense. ECDSA, you would never do Mimblewimble with ECDSA, and it wouldn't work. You wouldn't go very far with that. So Schnorr was envisioned for Schnorr. ECDSA came later when we wanted to do similar things because we were waiting for Schnorr. And of course, as luck would have it, as soon as we start having this ECDSA adapter signatures, we now have Taproot probably going live this year, fingers crossed. So hopefully we can chuck away this code as soon as it was developed, pretty much.
Yeah, but it's still good to have everything prepared in even now. Just just by the fact of the software existing, there exists the possibility that someone is actually using on the Bitcoin time chain, and that alone improves privacy of everyone. And it's this idea of maybe let's explore a bit more on that conclusion, because one of the nice use cases is basically swapping Bitcoin, right? So swapping to separate coins. Can you maybe go a bit through how coin swaps work with adapter signatures?
Yeah. So a coin swap, according to my terminology, is just to do like what we used to call an atomic swap between blockchains on the same chain. Okay. So atomic swap, it's a little easier to grasp actually as a financial transaction between, say, Bitcoin and Litecoin. Let's imagine they both had Schnorr, or let's imagine we have some adapter signature. We're using ECDSA adapter signatures. So we want to swap. So I want to sell my Bitcoin for Litecoin because I'm deranged, and you're taking advantage of that. What you have, this protocol, which is very simple and is known how to do with HTLC since a long time ago. It's one of the first Bitcoin protocols, the atomic swap, that was ever developed, which is kind of like cool because you forget that before, in the first few years of Bitcoin, people didn't have an idea, or there wasn't much of an idea that you could have protocols on top of Bitcoin, right? So this is like one of the first protocols that uses Bitcoin as a base layer to execute, or Bitcoin and Litecoin in this case. And so what you do is one party locks up their funds, right? The other party sees that, also locks up their funds, and as they lock up their funds, they both make sure that they have a refund condition, so they can both get the money back if a constraint is not satisfied by a certain time. So if one party aborts, we can always get the money back. So we have this set up, and then what we try and do is with adapter signatures, what we do is we take this locking signature idea, right? I've got the Bitcoin. I'm going to give you a locked signature with a transaction giving the Bitcoin to your address. Okay, and so you've got that, and then you also do the same to me. So we've both got these transactions locked on the same lock. Okay, that's important. They're both locked on the same key, the same public key, and then one of us, the person who went first, if I locked up the Bitcoin first, then you locked up the Litecoin, then with my key, I take the Litecoin from you by unlocking the signature. And then I publish that on the Litecoin blockchain. You get the key, extract the key from that, because we have this, that's the property of adaptor signatures. This is so crucial for these kind of protocols. You can extract that, and then you take that and you take the Bitcoin. So we've done this fair exchange. We've got this adapter signature, which gets us this fair exchange of signatures. And we use that to do, you get the Bitcoin, I get the Litecoin. If I get a signature getting the Litecoin, you get a signature getting the Bitcoin. And if I don't get the signature taking the Litecoin, you don't get a signature taking the Bitcoin, right? So this is, now what coin swaps are is just, we do this on the Bitcoin blockchain, and we don't, instead of trying to make money or trying to make a trade with it, we try and get privacy with it. So I have some coins, you have some coins, and we end up owning each other's coins, right? If I get a signature taking your coins, you get a signature taking my coins. And when we have proper Taproot Schnorr adapter signatures, we have that verification algorithm in there. We can use the Schnorr adapter signatures, and we can use MuSig, and we can make every transaction look like a normal address, like a normal Taproot output. Every transaction will have a normal Taproot output and spend using a normal Schnorr signature. And yet, after these transactions are done, these very, very dull looking normal transactions, I'll have your coins, you'll have my coins. And there's no way of telling that just by looking at the blockchain. So we could all be swapping each other's coins very often, and integrating that into, the way we work with our wallets, and then it becomes very difficult to know what the history of the coins becomes something of irrelevant, right? Similar to now, the advantage of that over a Coinjoin is you can't tell that the people are doing it. With Coinjoin, you get this, you sort of trash the history of your coins or intermix it with everyone else's coins. You're doing the Coinjoin, but you can tell that the Coinjoin happened. And so people get various emails when they deposit funds from a Coinjoin, or maybe like withdraw funds into a Coinjoin very quickly from an exchange, and they say, please don't do that anymore, or whatever. With this coin swapping, you can't tell. And that's the really powerful thing about it.
Yes, and again, this atomic locking up of Bitcoin under the same spending condition, right? That one party must reveal the secret, and that unlocks the Bitcoin of the other party. Again, this was possible with hash time lock contracts in the past already, right? And that worked well for cross-chain atomic swaps. But especially when you stay on the same chain, and especially if privacy and not linkability of those two transactions is your prime goal, then doing it with HTLCs is pointless, right? Because both transactions have the same hash time lock contract hash and pre-image. Therefore, instantly linking them, right, for any serious attacker. So the actual privacy win here is, again, that we move away from hashes and pre-images and towards private keys and signatures. And adapter signatures, just by the fact that the same crypto economical concept is possible without revealing that it was actually done, it's a massive privacy benefit for everyone.
Yeah. And it sounds like it's a trick. Like some people think of it like, oh, signature. This is a weird trick, and signatures should be signatures, right? And you should be messing around with them. That's something I've heard from a person, but it's actually a very deep and powerful technique. You can do the entire Lightning network. What you need, the core primitives for what you need in the Lightning network, the channel, just with adapter signatures, without any Taproots, Tapscript whatsoever. For example, like all of that stuff is mostly HDLCs and like all these pre-signed transactions. So you can just replace the HDLCs with adapter signatures, rearrange some things, and you have the full thing done without any script whatsoever. And so, yeah, this is a really, really powerful idea and excellent for just minimizing stuff that's on chain, which is good for our blockchain and our number of transactions we can process, but also great for the privacy. So it's like this win-win thing that we're just starting to take advantage of, and will be taking advantage of over the next years. And there's something I want to go more into depth on the coin swaps thing, because we can actually do even better than that protocol. But I was wondering if you want to continue on with DLCs, or if I should go on to this.
No, I think let's first delve down deeper into adapter signatures, and coin swaps is the prime thing. So I'm curious why you're excited about the advanced Coinjoin magic.
Well, we can do even better than that, okay? Because the problem with the coin swap, right? If we do a coin swap, you and I mean, I know that those coins were swapped, right? What if I'm if I'm Chainalysis, right, and I offer coin swaps? I now know the history, right? So it's like you've got to make sure that the person you're doing it with is not going to leak that information to anyone, or is not using that information against you. So coin swaps are nice, but it would be great if we could do it even in an even better way. And the way we can improve on that is if let's say you're the Chainalysis guy, right? If you're doing two coin swaps at the same time, or roughly, or if they're overlapping times, that you don't know which incoming coins to you were linked to which outgoing coins.
Yes, that's this concept of partially blind atomic or adapter signatures, and therefore partially blind atomic swaps.
Well, there's a whole the terms that I'm not sure exactly what the correct terms will be, but we call it like a tumbler sometimes, or like a mixer. Where mixers are usually like these central parties that do it, that could be run by Chainalysis, and could be and have your money confiscated as well, which is another problem that actually happens to people. Whereas what we could do is with these blinded coin swaps, as you put it, or these tumblers, is have them going there's no custody, so there's no chance of losing your coins. And if the tumbler is doing the protocol with multiple people, it cannot link the coins. And that's like quite a bit. It doesn't. Now you might be thinking that that's actually not such a big improvement, because the tumbler maybe just be doing the protocol with you. But if tumblers get used to the point that there's a few of them that are have a well-established reputation, you can sort of catch malicious behavior, or catch that targeting kind of attack, because they will reject to do to tumble your coins for you. They'll reject to do the coin swap with you, because they're trying to reduce the number of participants so they have a smaller anonymity set. So you can sort of catch this malicious behavior, and you have the same problem with coin joins. Okay, so the person coordinating the coin join may just refuse on a network level to do it with anyone except for this person who wants to do with this UTXO, right? And then the coin join ends up just being a bunch of fake inputs and outputs that are owned by the coordinator of the coin join, actually. And the only legitimate one is this guy who's trying to get anonymity or unlink doing some to break his history, but actually the coin joiner knows what the history is, because they were targeting them in this kind of attack. So you have the same problem with Coinjoin, but yet we find Coinjoins in practice don't have this problem happening too much, right? You know better than me, but this isn't. It seems like a theoretical concern, not much of a practical concern. You can tell as a user, you'll eventually figure it out if they're doing this kind of targeted attack. So if we, under this practical assumption, we should be able to get these tumblers. If we have an open research problem on how to do this, and this tumbler idea involves adaptor signatures and blind signatures and MuSig all sort of joined together. We don't. The problem is verifying that it's secure and getting a proof that can all go together well. But if it can, then we can get these like sort of blinded coin swaps. And
Yes.
that would be quite a big thing, because not only unlike Coinjoins, which only work on layer 1, this can work on layer 1 and it can work on layer 2. You can do these kind of tumblers with lightning payments. So you can decorrelate if you have a lightning node and identity on has been received a lot of payments, but you want to transfer it to your own personal node, right? To take your profit or whatever. You risk, if you risk linking it, if you don't do things in the right way. And one way to do it, maybe to just put it through a tumbler on a layer 2, and to make every payment, or even to make every payment you do, go through the tumbler first. And then even if the person has a de-anonymization technique for like Lightning Network, which you can heuristically kind of do sometimes with various probing attacks and things like that. This one at a cryptographic level gives you that guarantee that the incoming funds and the outgoing funds are unrelated to each other strictly.
Yes, I see. So here we kind of have a client and server relationship in a sense, right? And always here, right? If there's only one client for the server, then there is no privacy, right? The anonymity set is 1. The nice thing about Coinjoins is that the user can actually verify how much on-chain transaction fees the other participants have paid. And this gives him an actual real economic cost for a Sybil attack that even the coordinator has to pay, right? Coordinator has to pay mining fees too. And this is, I think, a very, very meaningful privacy metric. How much on-chain fees would an attacker have to spend in order to Sybil you? And we actually use this in Wabi Sabi for efficiency and optimization reasons.
This would be an advantage of Coinjoins over this kind of coin swaps, right? Yeah.
Right, because with a coin swap, one user does not know the other coin swaps of the same coordinator, because they are all not linked publicly, right? That's the whole good thing about coin swaps. So this means that a new service provider could spin up, could claim that he has thousands of users all the time, but actually you're the only one, right? And there's no way for you to actually verify that.
Yeah, I agree. I didn't think about that till now. That's a really good point. So we cannot necessarily rely on the success of Coinjoins to know that these coin swap kind of protocols will work out.
Yes,
but I have a feeling they will. Like
I do too.
I have a gut feeling.
I think it's very powerful, and I think there are other ways to make a economic cost for an attacker. I mean, Chris Belcher is pioneering the fidelity bonds idea, right, which would actually create a real cost in form of opportunity cost to attackers, which is useful, right? But again, the gist of this partially blind coin swap is that the client or the server cannot tell which client deposited, or he cannot link the deposit of one client to the withdrawal of the other client, of the same client. And again, it's non-custodial, meaning these deposits and withdrawals happen atomically, which means they are logically interlinked, right? But it does not mean that they're temporally on the same time. And actually, as a user of such swap service, the longer you wait between depositing your money inside and withdrawing it out, the better, because presumably other users start depositing in, meaning that your anonymity set increases as time passes and more users deposit and withdraw their Bitcoin to the swap.
Yeah, well put. That's the really interesting thing about it. And you can see, I think you could have these numbers run up in the weeks, right? You could deposit something early in the week, and then next week you finally decide you want to get that money out to give it to someone, you take it out then. And it's going to be a really tough to figure that out from the perspective of the tumbler.
Yes.
That's a really cool thing about it.
And there was one nice collaboration with Ruben Somsen and me to figure out how to batch together blind atomic swaps with succinct atomic swaps. So the idea of succinct atomic swaps is to actually give away a key as this locking material, right? And because then the actual private key is given away, you have the full possibility to spend the coin, right, without actually making an on-chain transaction. Right? The classical adapter signatures need to be on-chain, while if you give away your private key, that can be done off-chain. Right? So this cuts down the actual on-chain footprint of these swaps from 4 transactions to 2 transactions. And very interestingly, it increases, of course, the speed. And the reason why we thought about this was like specifically for the use case where we have a service provider being that central swap coordinator or actually provider, liquidity maker. And he is kind of tasked by the client with doing on-chain privacy for him in kind of a service provider way. That if the user wants to receive Bitcoin from a non-private source, like his friend, the exchange, whatever it is, but he wants to be able to spend Bitcoin instantly and privately so that the sender of that money cannot look at his future transactions history, then the swap provider can do Coinjoins in advance, for example, generate anonymity set of the coins that are there, right? And have then a pool of UTXOs ready to be swapped with potential clients. And now when the client gets paid, the address shown that the wallet shows that the receiver gives over to the sender is actually already the funding transaction for that succinct atomic swap. Meaning that any received transaction gets instantly deposited into that swap server, right? That where already some pre-negotiation was done. And then the secret is revealed, or the key is forwarded, that gives the client the ability to spend a coin from the server, right, of that value, again with the anonymity set of all users, of all clients that the server has over time. And I think that leads to quite smooth UX, that you receive any amount of money and you can instantly spend it completely unlinkable with high anonymity set coins.
Yeah, that's a really fun idea. I hadn't thought about it like that, but that's a really cool idea. I like that. Ruben has a very good mind for these kind of problems as well. He comes up with things I never would have been able to come up with, and that a succinct atomic swap is one example that's a really big improvement in the atomic swap, but where I thought there would never ever be any. So this, like you said, it can cut down the number of transactions, and this just from a UX perspective is even a big improvement. And then this idea you've just told me there is like, yeah, that's being able to load up incoming funds ahead of time and just like have them be totally unlinked to me as a sort of a receiver of funds. That's very cool. And no one can really tell you're doing it, I think, right? If you're an exchange doing this, you could load up the funds into the tumbler and then get them out and deposit. The user would see the deposit, but the funds that you end up with were never linked to the user. Use UTXOs.
Yes, and like one of the problems is with coin swaps, right? That you don't destroy the transaction history, quote unquote, as a Coinjoin does. Right? It's just impossible to follow transaction history in some attack vectors. While with coin swaps, like you just swap the transaction history. You don't break it. Right? So the client ends up with the transaction history of the server, and the server with the transaction history of the client. So
that's right,
depending on how each of these parties actually behave, that might be an issue, right? So if you swap your Bitcoin from a KYC exchange with someone like an anonymous person in cyberspace who's then gonna spend it on truck trafficking, then this might lead unwanted scrutiny to you, right? Because on the blockchain, you got the coin from a KYC exchange, and then it went into dark markets. that's a problem. And the same in that use case example that I spoke above, with having that coordinator kind of outsourcing the on-chain privacy. Like when you from your exchange swap into that server wallet, the server will do something with that money, right? Either swap it on to other users, which then would swap the on-chain transaction history of two users, which I would argue is not good. So I would prefer that swap provider to make a Coinjoin instead, breaking that history, right? Not putting his customers into like the possible attack of misguided judgment of that swap. But of course, that again reveals that the client was talking to that server who then did Coinjoin, right? So the exchange would still find out that you did Coinjoin, even though it wasn't you, right? Because you swapped your transaction history.
Yeah, there's it is, we do not know yet the impact that this will have on the actual practical interactions, because obviously privacy is like a practical thing, right? You want privacy, but then you also don't want to be, inhibited in what you're trying to do. You're trying to hide from, you want to interact with people you want to interact with without leaking information. But then the fact that you're trying to hide information may still be possible to recover some of that, depending on how clever they are, right? Depending on how much effort they put into observing the history of these transactions. And yeah, like you said, you may get someone else's UTXOs which are not which are banned, and then you end up in trouble. So it's I guess the hope is just to decrease the usefulness of applying the techniques to actually find out real information. If you start punishing people sort of willy-nilly randomly, for no fault of their own, because they use the Tumblr service, then your business is at a disadvantage to those who don't, right? So that's that puts the pressure there on the business to not behave like this. Better than other, because they get pressured by the authorities, but then if you make it really difficult for them, I guess it ends up in a place where there is practically better privacy and smoother interactions. I hear that like some exchanges want you to use Coinjoin, so they cannot tell what you've been doing. But I guess that'll change as the Chainalysis changes and all this stuff. But having that, being able to do that protocol, I still say is quite an important achievement from a privacy perspective.
Yes, again, just the optionality is great.
Yeah, having the option, and you can also do it on layer 2, right? That's the other important thing to me, is being able to have payment hubs, right? Which are just passively mixing the payments, and they cannot be linked to you, no matter how good they are at, looking at probing the network, the Lightning network, and putting malicious nodes in there. You can get that guarantee and just load up funds like you would on chain, like into the payment hub, and then just extract them and make the payment later on when you need to, in an unlinkable way. So depending, we can't know what you would know much better what the effects of this would be in terms of practical users, using this kind of thing on chain. But then the attractive thing is that it applies off chain as well, and so that scales. The research work is not wasted if it ends up being like more trouble than it's worth on chain.
Yes, exactly. And here again, like transaction efficiency, block space efficiency is a high importance, and that's why succinct atomic swaps, for example, super interesting, right? Let's maybe also get a bit more into payment channels, right? Because this is somewhat of a more specific type of swap transaction, I might argue. And there are a couple cool ideas, right? Like, of course, Lightning Network payment channels, then Tumblebit payment channels. What else? Asynchronous autonomous locks or something. Like, there are a lot of private blinded payment channel approaches. Kind of which one of them is on the cutting edge right now?
For privacy, from a privacy perspective, my favorite idea that I've seen is the Tumblr one. So like you have the payment hub and you send money through there and it just gets mixed with everyone else who gets sent through that there, and the payment hub cannot link the incoming payments to the outgoing payments. Okay, so from a privacy perspective, then that's the most interesting thing. But from channels, we have all kinds of interesting research coming up, and I'm having my own ideas and trying to go different directions. So that's a whole big topic. Do you want to get into that?
Would be interesting to at least scratch the surface of where you're currently at with that thinking.
Well, okay, let's talk about one that's currently on my mind. Tomorrow we're doing the Sydney Bitcoin Socratic, and we're going to have a presentation from a new paper called Blitz, and they've managed to do payments without HTLCs at all. Okay, so just using the UTXO transaction structure and timeouts and stuff, they've managed to do payments without any HTLCs. So that's obviously that blows your sort of starting point for most thinkers on this space, right? If you can do it without HTLCs, well, what else is there? So that shows you how broad this the design space is for payment channels, right? Mm-hmm. This thing that we've been doing since the beginning with HTLCs and what we've just been talking about with adaptor signatures, you can do it without even those things. To give an intuition of how.
Like, how does it actually work? How efficient is that?
Yeah, I'll give you the trick, right? The shtick. The idea is, if I want to make a payment through you, right? Instead of doing what we do with HTLCs, which hash time lock contracts is like I give you a thing and the ability to take the money if you reveal a secret, same thing with adaptor signatures, or I get it back on timeout. The trick is I give you money, right? And by the timeout, instead of I'm getting it back, you get it. So it's the reverse. I'm going to give you money, and if I haven't canceled the money by the timeout, you'll get it. Okay, so instead of that's the opposite way, in that I give you the money, and if you haven't done something by the timeout, I get it back. It's the opposite way. So that's how it starts, right? And so you, given this offer of money that you're going to get after a certain amount of time, unless I cancel it, you go and try and find the person who would cause me, if them receiving the money not to cancel it, right? If it gets to my destination, I won't cancel it. And so you go and forward the payment with the same kind of condition. Here's some money. You'll get it by the timeout if I haven't canceled it. So it keeps going throughout until it gets to the destination. The destination tells the sender that they've got it. And then the sender doesn't. Then the sender says, "Okay, I'm not going to cancel it." And there's a way of fast. There's an idea in the paper that you don't have to wait the time, right? So you can just say the sender can withdraw their ability to cancel it, and then you can just update the channel so that the funds go straight through.
And how?
And so that's the basic idea.
And how do you forfeit that claim to cancel the transaction?
How do you execute the claim, or how do you execute the canceling, right? So the big problem is, how do you make sure that all of the things cancel at the same time? If one cancels, how do they all cancel, right? Mm-hmm. And so you have this kind of funny transaction that has a lot of outputs on it, and it gets sent around to each party in the path, and they add their let's say a cancellation output onto it. And so if the sender decides that this payment is not going through, and only the sender can do this cancellation, they're the only one who has this transaction, and it's just really their own transaction that they made up, but it spans to all these outputs that were chosen by the different hops. And so they put it on the blockchain, and that has an output that will allow you to double spend or cancel the payment going through. Okay, so if you if you have that transaction on chain, you can all cancel now. You can all go put the cancellation now. There's a lot of timeouting and stuff like that has to go. Making sure timeouts don't overlap and things like that you have to do to make sure that works, and that you make sure that everyone has a chance to cancel. If one person has a chance to cancel, likewise, if one person cancels, everyone cancels, right? To make sure that you have that guarantee, it takes a lot of trickery, timeout, staggering, and relative and absolute stuff going on. And I can't explain it even off the top of my head, but I've read through the paper several times. And I think it does work now. So I didn't expect this kind of construction to ever work, but I think it does work. So it's kind of remarkable, right? You can get payment channels without any HTLCs, we think.
Yeah, that's fascinating. But it does seem to create more UTXOs in the worst case, right? Which is a bad thing.
Yeah, if the TX error goes on this thing called the TX error, which is the error, the cancellation transaction goes on chain, then it's quite some outputs that went on chain, but they're not large outputs, I guess. And I guess you can eventually just spend them. I mean, I don't know if that helps, but I guess they're like dust outputs. Yeah, you're right. That is one thing, and I'm going to ask the authors about that tomorrow. Like, are you just creating a bunch of toxic waste on the blockchain with all these cancellation transactions, or what? So that'll be my objection. Thank you for that idea. But okay, so the important thing is, the thing we preserve is that if this transaction does go on chain, not everyone has to go on chain, right? Because that would be pointless. Only the party dealing with the party not cooperating. As soon as everyone else sees the cancellation, they can all just cancel off chain. They don't have to go and spend from the cancellation output. As long as they're cooperative with each other, they can cancel off chain, and just carry on. That's a cancelled payment, and carry on with the next one. So not everyone has to just go on chain because one person goes on chain. So they managed to preserve that. And then the supposed advantage of this is that you do not have to have these staggered time locks like you do in HTLC payment channels or Adaptor Signature payment channels, where each hop has to put on from the first hop has to be a longer timeout than the last hop. The last hop has to be the shortest one, and each hop has to get shorter towards the last hop, meaning the first hop has to have a very long timeout. With this, you don't have that. The amount of time the funds will be locked up for is the same for every hop along the way. So you don't have this extra, you have much less collateral. The time value of the locking up over time is much less, right? The amount of collateral you have locked up multiplied by the time you have it locked up is much, much less than in a typical payment channel. So we say it's more efficient from a collateral perspective.
Aha. Yeah, interesting trade-offs, right? In the best case, you can make more routes per minute or per whatever time metric, because per route the sats are locked up less. But then in the worst case, maybe more UTXOs created. Yeah, I mean, fascinating. There's so much research going on in the space. So many different prioritizations and optimizations can be chosen in the trade-offs vector. That's awesome.
That's just a great example to show you how broad, like, the design space we're dealing with is not what we thought it was originally, and now we've got this other stuff, and it's really cool to see all these researchers with different ideas coming into Bitcoin, right? And applying their totally unique ideas, and coming from unexpected places, like not the usual places, right? So that's a really interesting new development, I'd say. If it works, we can see if we can build it, right? And this is one of the things, I'll have to build it to see if it works. Though from reading the paper, I think it is solid. Yeah.
Yes. So actually, I like the code, right? That's where the whole magic manifests into existence.
And then you start to ask questions like, how is this even possible? This doesn't work. And like, this is actually, sometimes you go to the person who had the idea, like, this is not how Bitcoin works, because it's really all the different rules and stuff. And one thing they suffer with is you can't invalidate a transaction after a certain amount of time, right? That's one of the ones that is a sticking point. You can only validate transactions, check that the time is higher. So this kind of subtle, this weird nuance and knowledge of the way Bitcoin works is really necessary to build these things. And sometimes, you have to. Sometimes things don't work even you only figure out at the last minute after you've been working on it for a protocol for a long time that just Bitcoin doesn't work like that, unfortunately.
Yes. So it turns out Satoshi Dice was a bad idea.
Well, me personally, I love Satoshi Dice. I don't want to start up a whole controversy, but I thought that was the most amazing thing. From an engineering and blockchain sanity perspective, it was not a good thing, but I thought that was one of the things that early on made me think Bitcoin was incredible before I really got it. But the fact that I could just send money to an address, that magic of that feeling, right?
Mm-hmm.
That I don't have to make a login, I don't have to send my documents, and I can just do some fun gambling or make a bet on something. You never go back to thinking the same way about Bitcoin after for me, I never went back to thinking the Bitcoin the same way after I saw that, because that's encapsulated rhetorical freedom that cannot be taken away,
Yes,
it's technical freedom. I'm sure that excites you as well, or even though the design of it wasn't a bit bad. The kind of demonstration that it showed, right? Yeah. And its success, everyone, I think 1 million Bitcoin went through their address.
Yeah, it's fascinating. That the concept of using cryptography to make gambling more efficient is actually a very interesting one, and that's a perfect segue to actually talk about discrete log contracts because their prime use case is basically gambling, right? So
that's right.
How do we get from adaptor signatures to discrete log contracts?
So adaptor signatures. So we mentioned that these adaptor signatures are like a signature encryption, right? And this is basically the way that discrete log contract uses them. So this whole leak, you reveal the locking thing, locking key when you unlock it doesn't really apply here. So we're just talking about encryption. And so the very simple way it works is we both put money into a transaction, both put money into an output. We're making a bet. Let's say it's on the NBA or on the price of Bitcoin or whatever. We both decide what are the conditions of the bet, and in what conditions, what apportionment of funds there is. So what portion of the funds do I get? What do you get? Under which condition? And so these conditions are expressed as, let's say, public keys. Each condition is like a public key where only the oracle knows the secret key. And so what we're going to do is, under each condition, we're going to take the public key associated with that condition, and we're going to encrypt a transaction that spends for our joint output and apportions the funds according to what we've decided. And that's all we do. We create a joint output, we both fund it, we encrypt all these signatures to all these different public keys. Eventually the oracle will reveal one of the decryption keys, the secret key for one of those public keys. We take that secret key, or the winner, whoever feels enthusiastic about that being the outcome, says, yeah, I'm glad this happened. It decrypts the transaction they have and publishes on the blockchain. So we have this very simple 2 of 2 multisig, which when we have Schnorr will just be a single Schnorr public key. And then once the bet is settled, we have, once again, a single transaction spending it, from it looking very normal and boring. But off-chain, obviously, there was this big, between you and I, there was this big set of transactions we both jointly signed to map these conditions from the oracle into onto these the particular portion of funds we wanted. Unlike Ethereum, let's say, because Ethereum has a lot of oracle stuff going on, all this data, unfortunately, because it makes my skin crawl to think of all the data that goes onto the Ethereum blockchain. So all this, when you, in other systems, the people that have decided that the way to do it is to put actual data onto the blockchain, and you can have your smart contract can call and request data about this event, and some oracle will actually insert it on the blockchain, meaning your blockchain is full of data about the real world. Like it's like a database about what happened, which I guess could be cool in one way, but from our principles in Bitcoin is very not cool. Instead of having that, we have just these two boring transactions on the chain once again, even though we mapped this with the help of the Oracle, this complicated real world phenomenon. We mapped it onto the blockchain using two very normal boring transactions, just using cryptography to bridge these adaptor signatures to do this, to bridge the gap.
Yeah, right. That's great to have these smart contracts unchained, right? To let them actually float really off chain with client-side validated state, right? Where we only use the global base layer consensus for the actually important part, right? Was it successful or was it not, right? And I think that's a very powerful architectural concept, and DLCs for sure deliver on this. So the Oracle kind of has to commit to the potential outcomes that it wants to sign in the future, right?
Yeah. So this is where the sort of innovate, like, so the big innovation, I'd say, from the paper is actually just the concept, right? So just doing things properly without shoving data on the blockchain or having oracles interact with the parties. Because the other thing we haven't talked about is this: oracles publish these public keys, but there is no interaction with any particular party. They just publish publicly. That's a really awesome property, because it means you have, oracles are trusted, they're trusted parties, but we can call them oblivious trusted parties because they do not know which users are using them and to do what with what they're publishing. So the oracles are just these publishers, and when they have an event in mind that they will attest to the outcome of, we say that the oracle announces an event. It says, okay, I'm going to attest to the outcome of this particular event, that whenever it transpires. And to do that, we don't just get the oracle to send a list of public keys. Okay. And the only reason we don't do this is just the main reason we don't do this is just for efficiency. We don't want to, if we have an event like the Bitcoin price with potentially, 100,000 different outcomes, if we do every dollar for up to 100K, we don't do that. Because that would be a very large thing to communicate. So the technical trick from the original paper is to what we now call anticipated signatures. So we talked about Schnorr signatures before. The Schnorr signatures are the R and the S value. Okay, so the R goes in and gets hashed, and then the signer gets an S value from that and puts it with the R to sign the message, which also goes into the hash. Now, what we can do without even the signer revealing this S value to us, if they just publish the R value, right? So it's like a half of the signature, just the R value, the public nonce, or this random nonce, we can then hash that with a message, and we can't figure out what the S value is, because that would be insecure, obviously, if we could do that. But we can figure out the image of the S value. Now, the S value is occupies the same space as a secret key, and the image of the S value is like a public key. And so what we can do is have the oracle just publish an R value. This is how it was in the original paper. They just publish an R value, and then we look at every possible attestation they may make for the event, like every price of Bitcoin, let's say, and we put every price of Bitcoin is its own message. And then we just anticipate what each of the S values would look like. What would be the associated public key of each S value? So the oracle only ends up publishing a single R value. Now, does that make sense?
Yes, but why is that done? Is that for efficiency reasons, or?
It's mostly for efficiency reasons. That's the main reason. There is another trick. Okay, so there's another trick to make. So if the oracle attests to two different things, two different S values, we can recover against the same R value, right? Against the same announcement, they retested two different outcomes for the events. So they effectively produce the S value and a signature for two different messages. Then we can extract the Oracle secret key from this. That's another reason you may want to go with this. It creates a kind of cool punishment mechanism where if the Oracle behaves maliciously, it's not the only way the Oracle can behave maliciously, but one of them is to attest to two different events, two different outcomes. Excuse me. They publish, let's say, one publicly, but then they use their other one that they can create because they have their secret key, and they take money from a bet that they were a party to before they publish the one publicly. Then, okay, we bring in back in our adapter signature. We can actually use that unlocking trick from the adapter signature and then to extract the key that they used to unlock the event that they took. They stole money from us for an event that didn't happen, an outcome that didn't happen for the event we were betting on. Manchester beat Liverpool in reality, but they bet on Liverpool beating Manchester. They publicly tell everyone that Manchester beat Liverpool, but they take the money for the Liverpool beat Manchester from our bet because they produced this secretly. And then what we can do then is with this adapter signature locking thing, when they unlock that money illegally, we get the unlocking key, which was the signature, was the S value. And so now we can take the public attestation that was told to everyone publicly and take this attestation scalar we extracted from the money that they stole from us and combine them and extract the Oracle secret key. Okay, so that's another reason why deriving all of these public keys, these public points, these attestation points, I sometimes call them, from a single R value and all the messages using this anticipated signature scheme is a good idea. The compression is the most important part, but there is this additional punishment mechanism that can exist. I think in practice we're not too enthusiastic about it for various technical reasons, but that's the two main ideas there.
Yes, and so the one important thing to point out here is that the Oracle does not leak its Bitcoin private key, right? So you don't leak the spending condition to how to spend your actual Bitcoin, right? But you leak the private key of this off-chain protocol, right? So this is not that we can steal the money or take the money of the Oracle. It's rather that we have the private key, which should be a secret, and just by the fact that we have that private key, we can prove to others that, look, this Oracle signed two competing messages.
Well, yeah, there's that. I mean, that we could do the proving without this. Okay, so we could get rid of this leaking the private key and do the proving bit where we just prove that the Oracle signed two different messages without leaking their private key. That's possible. But the leaking the private key thing, it's kind of like a scorched earth devastation thing where everyone can be the Oracle now and sign whatever they want because they have the secret key. It's kind of it's a kind of a dangerous thing, right? Because it doesn't punish the Oracle so much as everyone using the Oracle. So that's
true, right?
The Oracle's business is over. Let's say if they make a business out of this, it's over. They could put money into this public key that they would lose the secret key to if they equivocated on the outcome of an event. But is it really a good idea? That's most of the people working on it don't think that's such a good idea.
Yeah, right. For example, we have 100 users using the same Oracle. Right now, the Oracle publishes one public message about how things are, right? And the first person sees this. And then let's say the other people did not yet see this, right? And then the first person claims his DLC contract based on that signature. Right? And now let's say the Oracle leaks the other part, or writes a second signature, therefore leaking its private key. Right? And let's say the second out of 100 users now has this and can calculate the actual private key. This still means that there are 98 unsettled open DLC contracts out there that rely on that on signatures of that private key, and especially when we're talking about Bitcoin price predictions, right, where there are many different values, like doesn't that mean that all the other people who have not yet settled their contracts are actually at risk of settling them at a wrong state?
Yes. That's why, yeah, that's exactly it. But what if it was just a mistake, like a technical error from the Oracle, and then all the users get hosed because of this thing? So it's like not really. It's interesting theoretically, and certainly good idea to put it in the paper, and try and preserve it, maybe theoretically, but maybe in practice we don't do this.
Yeah, really, this is not a punishment for the Oracle. That is really a financial risk for all the users of the Oracle who didn't yet settle it.
I would say so. We pretty much everyone agrees on that point.
Okay, cool.
Yeah.
Yeah.
There are a number of reasons that actually. So, if you're interested in this is ongoing research. There are some reasons why you don't want to do that signature idea. The way it works, right? So with this nonce up front, one thing people might know is that you remember MuSig. We talked about MuSig, and there was an initial version of MuSig that was 2-round, and it was not secure. Okay, and the reason it was not secure is because your nonces are being published. The reason it was not secure because we're doing these nonces. So in order to produce a joint signature, we exchange nonces, right? So this nonce, it turns out this nonce exchange protocol is very sensitive. So if you do it in 2 rounds, as was originally envisioned, and I send you a nonce and you send me a nonce, right? That's the 2 rounds. And then we create a joint nonce by, let's say, adding them together. This is insecure because what I can do with that is look at your nonce and choose my nonce adaptively. And that changes the hash, right? And let's say, and another insecure thing is we choose a nonce up front, and then I choose what the message we're going to sign is, right? So when you do the MuSig protocol, you got to know what the message you are going to sign is up front before you start the protocol, okay? So this protocol we have here, if you look at the security, which I've done a bit, it ends up being insecure in a few ways. The reason is you put this nonce up front, right? This half of the signature goes up front, and then you attest to the outcome of an event. But the Oracle doesn't decide what the outcome of an event is, right? If you're feeding, you may be able to feed the Oracle outcomes of events. Like if you can tell the Oracle what to attest to, and arbitrarily, you may be able to get it to do on a cryptographic level to, let's say, forge a signature. You may be able to forge an Oracle signature because they put this nonce up front, which is not what you're meant to do in Schnorr signatures. In Schnorr signatures, the signer is meant to generate their nonce, given a message, generate the nonce, make a signature, create the S value. But here we're putting the nonce up front and then letting someone else potentially choose what the message to be signed is, which is what you cannot do securely. There are various reasons why it's not as bad in this case as in the case of MuSig, but it's something we're looking at changing how this works. And it's an open research problem to replace this scheme or to figure out how to do it securely.
Yeah, it really does seem that, I mean, for one, the concept that we've built already as of now are mind-boggling, crazy good already, right? But there are so many open problems to be solved and to be discussed. And you've actually just recently started bitcoin-problems.github.io, which is a repository for open Bitcoin research problem. Now, this sounds like a really great idea, but what is it actually about?
Yeah, it's about giving people outside the day-to-day Bitcoin research community, people listening to the mailing lists, people at Bitcoin companies doing research and development, and giving some tasks or some helping to focus research of the greater academic community towards things that would be impactful for Bitcoin users and the evolution of Bitcoin itself, right? often there's like a sort of disconnect, right? Where people are generating ideas that are Bitcoin related or, maybe applicable to Bitcoin, but they're missing out on instead. Probably there could have been something more practical and more useful that they could have been doing with their time. No matter how useful how cool their idea is, it may not be that practical right now. And not only that, but people may work on, like, let's say, Ethereum-based ideas because they don't know of any interesting ideas, any interesting problems related to Bitcoin. So what this website is an attempt to get really refined pages, just web pages for each problem that describe what it is and what would be the impact, and get all the mailing list posts and related research on that problem, so that if you're a PhD student or a postgrad, you can go to this and say, okay, read about it and say, like, I'm going to do my thesis on this, or I'm going to work towards fixing this problem. That's my hope. That's my dream. It also just gives a nice place for other Bitcoin researchers like myself to put ideas. But I'm trying to just say, like, listen, I've got these ideas and I'm not sure how to solve these problems, and people are putting, telling me about their problems, and I think these problems should be solved. I don't know if I could put it on my plate, so at least I can write it down. And then hopefully other people will write down problems as well, and we can have this nice curated list that if you're looking for something to tackle, you can just go and solve it for us.
Yes, right. Just knowing what the actual problems are, what are the important questions to ask. That's the core where you start. If you don't know that, then all your analysis will be wasted. Right. So this is great, especially for new researchers coming to see what are the open problems that really are pressing and that need to be solved, and that are difficult, right, and non-trivial. And where so far everyone is still not sure about the most optimal solution. This is a really great resource to get people going.
Yeah, I'm looking forward to some contributions for people, and I'm looking mostly forward to getting one of them closed and to figure out what that means and how that process works. How do we know when it's solved? As a kind of but I'm really looking forward, and I think hopefully sometime this year I'm going to be able to say this research problem is solved.
Yeah, right. That would be great. And then hopefully we can solve more problems than we add to the list. But it seems
Right.
we're on exponential growth here with more and more problems being added.
Yeah. One day Bitcoin will be so boring. There's no open problems, and but that's kind of the perception it has, right? Amongst some researchers who maybe not paying too much attention. Like, Bitcoin is kind of like a solved problem. I use proof of work, all very simple. Has signatures, and that's basically it. It's boring and it's a solved problem. Well, let's try and do some, consensus algorithm work with like a proof of stake kind of thing, or some weird snark proof contract thing for Ethereum. And really, like, there are really deep problems we have with Bitcoin, which is this, was a $1 trillion asset. Well, we're just going to say it's a $1 trillion asset. It'll be back there soon. And we have these big open problems that you can sink your teeth into, and they're really difficult, and they're really rich, and they totally deserve publication in academic conferences, in cryptography and journals and stuff. So let's change that perception. Let's show that the Bitcoin is actually the most interesting thing to work on as a researcher as well, because, like, it has the most impact. If you solve one of these problems, it's going to have more of an impact on the future of money than inventing new, slightly more efficient schemes for doing weird stuff on Ethereum. Obviously that's my biased opinion, but that's what I think is happening to some extent. Because I mean, I'm a little bit smart, but I don't think that some of these problems feel like no one is working on them apart from me, and maybe a few other people. And we need more people working on these research problems. And there seems to be like a lot of researchers around, just not focused on Bitcoin or not focused on these problems in Bitcoin.
Mm-hmm. Yes, I see. And I mean, for example, with Adam Polstra, like after years of researchers struggling to find these ways to verify, like a fair exchange of signatures, as he said, right? All of a sudden,
Mm-mm.
a Bitcoiner comes up with a brilliant solution just because he was thinking in that Bitcoin mindset, right? And solving an actual problem of the Bitcoin protocol, basically, right? How to do these swaps, these atomic transactions with signatures instead of hashes. Right? Very applied problem, very, very fundamentally important solution, and not just for Bitcoin, but for the whole cryptography space.
Yeah, that's right. We should, and although we're lucky to have Andrew, it'd be better not have to wait for Andrew to solve each of these problems, or someone from Blockstream, which is the current like research agenda driven development. Is like, we try and wait for someone at Blockstream to solve it. But I think, we have our problems because we're adding layers, right? We're adding a layer 2, and the number of problems now are becoming layered and growing in the same way Lightning enables many more users and many more payments. It brings up many new problems, and so we need to scale the problem solving as well as the transactions.
Yes, exactly. Pierce, you've heard it here first. Bitcoin is boring. There are no open problems, no innovation happening here whatsoever. Move along. No, like Floyd, this was a really great conversation. We really dove down deep into a lot of these cool, magical things that are now possible with cryptography, and hopefully that made the listeners even more bullish on Taproot specifically and what we can do with this, what this means for Lightning Network, for pay swap, for coin swaps, for tumblers, for discrete log contracts and gambling, like. Just that one single Taproot upgrade is so monumental and so prolific on many fronts, and we're just getting going. there are many, many more additional things that we will build on top of this. So yes, come and join us. Check out bitcoin-problems.github.io. Those are some important problems to be solved. So thanks, Lloyd, for curating them. And yeah, any final words? Where can the users find you?
On GitHub and Twitter, LLFOURN is my handle, and Lloyd.FOURN at gmail.com is my email, and I respond eventually. Come talk to me about anything.
Yes, eventually in 2 weeks you will have a reply back.
Yeah,
After
eventually.
all the problems are solved.
I'm really good I get to things eventually. Now, that's a really big improvement for me.
Yes, that's great. Okay, Lloyd, again, thanks so much for all the work that you do. Seriously, like you've helped me advance my understanding of a lot of these things quite a lot, and that's already leading to nice actual development and implementations of all these ideas. So yes, we're gonna make it happen. So thanks a lot for your theoretical input and also making sure that it actually gets manifested in cyberspace too.
Well, thanks a lot to you guys too, and Wasabi. Thanks for talking to me. Excited to see what you guys come up with.
Yes, I think we have a lot of opportunities to settle DLC contracts inside Wabi-Sabi Coinjoin transactions that also open a Lightning Channel factory instantly. Yeah, soon. In 2 weeks.